Hi, welcome to the 14th lecture on topology. Today we are going to do something very interesting. We are going to look at the collection of all topologies on a given set, okay, and look at some properties. Then we are going to play with it. Then we are going to introduce a new notion of a topology generated by a class of subsets of a given set. Okay, this is going to play a very important role throughout the course. Okay, so I will take a lot of time to explain the concepts so that demystify everything. Okay, please stay tuned. This is very important. That's all I can say. Yeah, let's get started. So let X be a set. Of course, as usual, we'll assume it's a non-empty set. Okay, let I do not know a good notation on here. Let me just see whether I can do. Okay. Okay, this be the collection of all topologies on X. Okay, notice that this collection is non-empty. Why? Because in discrete and discrete topology always exist, and it's also possible in discrete topology becomes discrete topology if the set X is a singleton, right? It's a, but so in any case this is non-empty set. Okay, not empty, right? Okay, now what we want to do is we are going to observe that, okay, what are the properties of this. So let me assume something. Again there is a notation here. Let S be a subset of T. This is a collection, a sub-collection of topologies, right? Then I want to claim let tau equal to intersection of, let us say tau naught or tau S equal to intersection of tau and the topologies in the collection is. Is that everything clear? So remember, each tau is a subset of P of X. So I look at all topologies which are in the sub collection as, okay, and take their intersection, which is, have you understood? Right. Now, does empty set belong to tau of S? Yes, because empty set belong to each and every tau in a script S. Therefore, empty set is an element. For a similar reason, X also is an element. Is that all right? Very good. Now suppose UI is a collection in tau of S, right? What do you think I want to check now? Can somebody guess? By now you should know, because just 2 lectures before we discussed about class of subgroups, class of vector subspaces, and class of closed sets, etc. Do you remember that? Yes, if you remember, then you should know. What do you want to say? So I want to know the union UI, I and I, this is also in tau of S, right? Okay, now let's look at, if UI is a subcollection tau of S, that means UI belong to tau. This is for every I in I. UI belong to tau. This is for every tau the topology in scripters. Please pay attention. Don't get psyched or intimidated by the notation. Keep the idea clear. So I have a topology. So I UI, right? UI is what? A subcollection tau. That means what? UI must be elements of each and every tau. Where is this tau? The tau is from S. Okay, right. You follow that? So fix a tau. Okay, fix a tau in script S. Then for all I in I, UI belong to tau. And since tau is a topology, intersection UI, I and I belong to tau. But for which tau? This is true for all tau in script S. So what do you think I have proved? I have proved I and I union. Okay, we are not talking about intersection. Union of open sets is open. That's what I should have in mind. I'm sorry for this mistake. This is all right because tau is a topology and UIs are open in tau, therefore union of UIs will be again open in tau. Okay, therefore this belongs to tau for each and every tau in tau of s, right? That means union UI I in I belong to intersection of tau in crypto, but this is by nothing other than tau s. Is it okay? Now let's look at U and V, which are in tau s. That means what? U belong to tau for each tau in S, and similarly V belong to tau for each tau in S. Therefore U intersection V, this belong to tau for each tau in S. Yeah, that means U intersection V belong to tau in crypto S. This is tau S. Yeah, so what do you think I have proved? Go back. What I did was I took a collection of topologies on X, not necessarily all, okay, a sub collection. And what did I find? Look, take their intersection, then I have proved that intersection is a topology. So this is similar to intersection of subgroups is subgroup, intersection of vector subspaces is again a vector subspace, intersection of closed sets is a closed. Similarly, intersection of topologies on a given set is a topology. Have you understood this? Please go through. For many of you the problem will be a second order because tau itself is a collection of p of x. Then what I am looking at? I am looking at a collection tau, a sub collection is, and right? Are you following? Okay. Anyway, so pause, review, see. Right? So we have proved intersection of any non-empty collection of topologies is again a topology on the set X. What is the natural question you would like to ask? Go back to my lecture on closed sets when I talked about subgroups, vector subspaces, ideals, closed sets, etc. Can you guess? So whenever we have said there is a collection of some mathematical structures and intersection of such collection is again a mathematical structure, the same mathematical structure, then the natural question to ask is, you give me a subset A, is there a smallest mathematical structure containing A? No. It will be, of course it will be abstract, but try to learn, because unless you begin to think like this, you will always be very afraid of such concepts. So what do you think I have to do? So I have a sub collection A of P of X. Remember what is tau? Tau is a topology, it's also a collection, right? Then what did I find? If I have a sub collection of topologies, okay, then intersection of that elements in the yes is again a topology. Therefore what is the question I want to ask? Give me a sub collection A, does there exist, okay, smallest topology, call it tau of A containing A. Just to make sure that you understand, let's start with some simple minded thing. Okay, you suppose I have a set, okay, let's look at the question itself. Let us try to understand, okay, by means of example. Suppose X is a set, right? What is that I am asking? I am suppose, let me say this is all singleton X in X, you understand, and this is a sub collection in P of X, right? Not, I am not talking all I am not talking about all subsets, only singleton subsets. Now what is the question I am asking? What is the smallest topology containing A? Okay, That means what? Tau A must be a topology which contains A, and if tau is any topology which contains A, then what should be the relation between tau A and tau? Tau A should be subset of tau. Sorry, tau A should be subset of tau. Yeah, that's what meant by smallest. Among all topologies which contain A, tau A is the smallest. Is the question clear? Right? For example, let's look at, suppose my X is R2, right? My script A, it must be a collection of subsets of R2. Let me say a collection of all lines. In R2. Then what is the question I'm asking? The same question. I want a topology tau A which contain this, and it is the smallest. Are you following? I just gave some small examples so that you will understand the problem, because many people may be kind of intimidated by so much of notation, scripters, etc., etc. Have you understood this? Yeah? Okay. Now the question is, why should it exist? Is it existence clear? Yes. Because you suppose you give me a collection here. Is there any topology which contains script A? Yeah. Let me say tau A to be all topologies. Tau is a topology on X. So that script A is contained in tau. Why this is not empty? Because tau discrete is always here. Discrete topology is P of X, right? That's always here. Therefore, the collection is non-empty. Therefore, what do I know? So if I look at tau A to be intersection of tau and say that tau is in TA, then this is a topology and this contains script A by construction. Do all of you understand? Because A is a subset of tau, each and every tau, where tau is in this family. And it's intersection of topology, therefore I know this is a topology. So what is it I have to prove? This is the smallest topology. Is it the smallest topology? Of course, yes. Suppose let's say tau prime is a topology which contains script A. Then tau prime should be in tau of A, right? Therefore, one of these tau must be tau prime. Therefore, tau A will be subset of tau prime. Do you understand that? Yeah. Therefore, tau A, okay, is a subset of tau prime. So it is the smallest topology. Yeah. Pause. Review. Proceed. Okay. Now what is the question I should ask now? Now that I have proved, given any sub collection A of subsets of a given set X, there exists a smallest topology tau A which contains A. Very good. So I have proved the existence. What is the next question I should ask? What did we ask about subgroups, or ideals, or vector subspaces, or closed sets? We want a concrete description of the collection thing, right? Let us go back to make you understand. This is supposed to be a topology course, but as I said, for me it's a mathematical course. Topology is one aspect of mathematics for me, so I don't want to miss the whole picture for a part of a picture. So suppose G is a group, right? And suppose my element A is a singleton A, right? Then what did I do? The subgroup HA is nothing other than this we saw. Do you remember that? And suppose R is a commutative ring with identity if you want. Okay, my A is a singleton A. What is the smallest ideal which contains A? This is what R times A as R varies over A. So this is an ordinary R, ring R. Okay. Yeah. This is what you call principal ideal. Now how do I know? I know such an ideal, smallest ideal containing, okay, ideal containing A exists, right? So if you give me A belongs to IA, and since this is an ideal, R is a ring element, then R times A must also be an IA. Do you understand that? Yeah. And similarly, n times A, that is A plus n, or if n is negative, minus A plus minus A plus minus A, n times. All of them must be in IA, right? But what we know is n times A is nothing other than n is, you can think of n as a ring element, namely n times 1. Therefore n times A is going to be, yeah, n times 1, this is a ring element into A. Yeah, these are the things algebra should have explained very well to you. Okay. I hope you know these things, right? Now let me look at the collection RA. Therefore RA must be in I of A. But what I find is this is already an ideal. This is very easy to check. Okay, check this is an ideal. So IA is the smallest ideal which contains A, but RA is an ideal which already contains A. Therefore the conclusion is IA must be collection RA as R varies over R. Okay, pause, review, proceed. This is okay. Unlike your algebra teacher, I did not define the principal ideal. I arrived at that principal ideal. Yeah. And the same thing with respect to vector subspace. Suppose V is a vector subspace and A is a subset of V. Then I know there exists a WA is the smallest vector subspace. I know it exists. Smallest vector subspace containing A. Right? Now what do I know? Suppose I start with any collection V1 to Vn in A, and say C1 to Cn in the scalars. Okay, scalar meaning, let me assume it's a vector space over R. Okay, over any field it's the same thing. Okay, then since V1 V2 Vn belong to A and A is contained in WA, then V1 V2 Vn are in WA, and therefore any linear, this is a vector subspace, therefore C1 V1 plus Cn Vn must also be an element of WA. Okay, this could be any collection. If you want, I am not assuming A is finite, right? Now if you look at this collection, call it W0, the collection of all elements of the form C1 V1 plus Cn Vn, okay, where n is over all integers and Ci's are scalars and Vi's are elements of A. Okay, that is all possible finite. What is this? This is collection of all possible finite linear combinations. Elements in A. Okay, this is very easy to check. This is already a vector subspace, and we know that all elements, this A is a subset of this, because I only have to take V equal to V1. If V belong to A, take V equal to V1, C1 equal to 1, or the rest are all 0. It has to be there. You understand that? Right? Now this W0 must be already in WA, but it's already a vector subspace containing A. Therefore the conclusion is W0 equal to WA. Right? In the last example what we saw was, if X tau is a topological space, A is there, we define what is meant by A closure, then we found out a concrete description. It is the set of different points. So look at all these 4 examples. Maths is beautiful. Okay, if you think of it as a unified subject, okay, not separate disciplines, compartmentalized. Then in each of the cases we know the existence of the smallest object of the required kind. Then finally what we asked was, and we also solved was, okay, a concrete description of the smallest object. the smallest subgroup containing a single element, the smallest ideal containing a single element, the smallest vector subspace containing a given subset, and the smallest closed set which contains A. You understand? So what we plan to now do is can I get a concrete description? Okay, right. Before going further, let us play with it for a while. Okay, we will give a concrete description. Before that, we will attend to the earlier problems which you looked at. Suppose my x is any set, my script A is okay singleton x as x varies over capital X. Now what is tau A? How do I find it? Remember, script A must be a subset of P of X, class of some sub collection of subsets. Okay, what should be tau of A? Now notice that it should see tau of A is a topology. It should contain all singleton. And what do we know? Since tau A is a topology, arbitrary union of open sets in tau A should again be in tau A. But then if you give me any subset E of X, then E I can always write it as a union of singleton X. Singleton X in E. Yeah? Are you following, or shall I erase it and write it again? Right? Therefore, what do I know? Every subset E of X, okay, implies E is already in tau of A. That means tau of A is nothing other than the power set of X, that is the discrete topology. Okay, so this is example 1. So we call this tau A is the topology generated by the collection. Generated by the collection A. Yeah, let's look at a second example. Suppose I take a set X. Okay, now my collection A consists of collection of all 2 elements. Yeah, now I want to know what is the topology tau A. Right, now you will see something very interesting happening. Okay, if I had done it's a very beautiful thing. What are the possibilities? X may have only one element, or X may have 2 elements, or X may have okay more than 2 elements. You understand? Because what is the collection A? Collection of what? 2 element subsets of X. X is just a nonempty set. Therefore, if X is a singleton, okay, then what is A? Is empty, because there is no 2 element set, right? Therefore, what is tau A? So you want the smallest topology which contains the empty collection of subsets. Therefore, this is indiscrete topology. Remember, script A is empty. Therefore, you are looking at a topology tau which contains the empty collection. It's not empty set. Okay, these are different. Do you understand? This is not what we are meaning. We are saying it's a collection of subsets. This empty set stands for the collection of subsets of X. So A must is the empty collection of subsets of X. Therefore, I want a tau A topology which is a collection of subsets of X. Therefore, what is the smallest collection which contains the empty collection? Namely, it must be a topology. Therefore, it must be the indiscrete topology. Yeah, please pay attention. If you have a problem, go through it again. Now suppose X and Y by 2 elements, right? Then what are the subset 2 element subsets? It's only 1. Notice that I have to do like this. You understand that? It's a collection of subsets. Each subset have 2 elements. Therefore, this is a collection. Learn to write this kind of thing, because these are the things which I find even MSc students do not struggle to write carefully. Okay, do you understand? A should be collection of two element subset. Therefore, this is a two element subset. It should be a collection. Therefore, I am putting another bracket. Do you understand that reason? Yeah. Now, what is tau A? So, you are looking for the smallest topology which contains this collection singleton here. But notice that this is nothing other than X. So, you are asking the smallest collection which contains X. Therefore, it is again the empty set and X. Therefore, in discrete topology. Do you follow that? Okay. Now let's look at a third thing where number of elements is greater than or equal to 3. Right? Now something interesting happens. How many of you can immediately see that? So I have 3 elements at least, right? Yeah. Then do you see that? Okay. Any 2 elements should be open, right? You understand? So let us look at A, B, C. There may be more elements. Take some 3 elements which are distinct in X, right? Then this must be in tau A, and this must also be in tau A. Now tau A is a topology. Therefore, the intersection, namely singleton B, must be in tau A, right? Do you follow that? What do you think I have proved? I have proved that, okay, give me any X in capital X, okay, since X has at least 3 elements, I can find Y and Z distinct from Y and two distinct elements, and each one of them is distinct from X. Therefore, I can form X, Y, Z. Therefore, I can form X, Y and X, Z. These are going to be in tau A because it's the smallest topology. That means their intersection, namely singleton X, must be in tau A. What do you think I have proved? Every singleton must be in tau A. That means the topology tau A must be the discrete topology. Yeah, right. Now let's look at X equal to R2, right? And let's look at my script A to be collection of all circles centered at origin. Okay, so what do you think tau A should be? Now take any 2 distinct elements in A, you see that? So this can be, this is nothing other than CR, where R is positive. Yeah, but I want 0 also, therefore let me say R greater than or equal to 0. Okay, all circles, okay, of radius greater than or equal to 0, right? Therefore, if I take this is R equal to 0, this is R equal to some R, okay, this is CR, and this may be my CS, C capital R. So if R is not equal to R, then CR intersection C capital R is empty. You see that? So this collection is or pairwise disjoint, right? This collection A is pairwise disjoint, right? And also we saw the union CR as R greater than or equal to 0 is all of R2. Therefore, this collection CR is a partition. You follow that? Yeah. Therefore, the tau A should be the partition topology. Okay. It's very easy now because the partition topology contains tau A. Sorry, partition topology contains all CRs. And if tau is any topology, then arbitrary collection of sub collection of CRs must again be in tau. But okay, Are you following what I'm saying? That is, if let A is a subset of 0 infinity, then look at CR R in A. This is an arbitrary collection of sub and A. You understand that? This A should not be, maybe I should not use let me call it B. Right? So this collection is a sub collection of sub A. Right? And in the partition, so these are in A, therefore, okay, the union CR, R is in B, should be in tau A. But remember, in the, are you following that? But these are arbitrary. What are the open sets in the partition topology? They are union of arbitrary collection of partitioning elements. Therefore, this also belong to tau partition, right? Therefore, every open set in partition topology is an element of tau A. We follow that. This is already a topology that is contained in tau A and tau A. Therefore, tau partition is contained in tau A, and your collection CR, okay, this is contained in this. Therefore, what do we conclude? Since this is the smallest topology containing CR, therefore tau partition should be equal to tau A. Okay, pause, review, proceed. A slight twist. Suppose my collection A all circles in R2, not necessarily concentric circles. Yeah, my X is of course R2. Now what do you think is tau A? Notice that one of the things you should remember is the topology means arbitrary union of sets must be in topology, must be again be in topology, and take two elements in the topology, their intersection should be there. So at every time, these are the things we should check. That will give us an idea how to look at tau A. Okay, please understand all these examples because this will help you my abstract thing now soon. Okay, now if I take two circles, what are the possibilities? Either they intersect at, you know that they intersect at 2 points, or they may tangentially meet at 1 point. Do you understand? Therefore, give me any point x comma y in R2, call it a point P, then there exists always two circles C1 and C2, so that C1 and C2 meet tangentially at P. Therefore, C1 intersection C2, okay, this must be in tau of A, but that is singleton P. Therefore, what is the conclusion? Tau A is the discrete topology. Okay, now the last example, I don't know, not know what is the number. Yeah, 4. Let us look at the last example. Let x equal to R, right? My collection A consists of all intervals of the form yeah. So what should be tau A? Can I describe? Is the question clear? So as you know, tau A, take arbitrary elements. Okay, if I take only minus infinity to A, arbitrary elements will be something like collection of such things, union A in some set B, a subset of real numbers, right? Then I know how to do that. Do you remember in ray topology you have seen? And similarly, if I have arbitrary collection B infinity, B in C, C is a R, again I know how to describe. Instead of right ray topology, it will be left ray topology. you must have learned it in from my course, right? Therefore all, so it should contain elements of the form again this and that, so that's not going to give something interesting. But remember, tau A is a topology. Just now I mentioned I should also check what happens to the intersection, right? So tau A, so if I take something like minus infinity A, that is in tau A, and if I take B infinity, that also should be in tau A, therefore the intersection should be in tau A. Do you follow that? Now what are the possibilities? Either A equal to B, in which case this is empty, or A is greater than B. Yeah, so this is my A, this is my B, alright. So what is the good thing? X must be greater than B and must less than A, therefore that interval is, maybe I should say B greater than A, right? I always like that way. Okay, A is less than B. In that case, this is AB, the interval. Okay, and suppose other way around, the same thing, right? Suppose B is less than A, then it's the same thing. Have you understood what I'm saying? Yeah. So that means tau A should contain all intervals of the form AB where A is less than B. Do you understand this? Now these are open intervals in R, and therefore arbitrary union of open intervals must again be in tau A. But arbitrary union of open intervals in tau A is nothing other than tau U, the usual topology on R, because this consists of all arbitrary union open intervals. You understand? Yeah, because any open set, okay, if you give me an open set U in the usual topology and you start with an X in U, then I know it is of the form X minus epsilon X, X plus epsilon X. Okay, there is epsilon positive, so that X minus epsilon, X plus epsilon is contained in U, right? Therefore it's union of such things, right? Therefore it's arbitrary union of open intervals. Therefore tau A should contain tau U. Have you understood? Now notice that tau U already contains A. What is our A? Look at that. A consists of either all right trace or all left trace, right? And we know that they are open in the usual topology. Yes? You understand? Therefore, what is the conclusion? Therefore, the conclusion is tau A is nothing other than tau U, the usual topology. So P or P. So I can keep on going, but I think it's time that I should. Now, what is the concrete description? Okay. So if I understood what I said, you should show that tau A should contain empty set and X. So how will I get it? Right now, how do you think intuitively all elements of A and take arbitrary union should be there? Therefore, I should expect. Let us look at U in A. I want it to be X. Are you following what I'm saying? Let us look at the collection A. Let me assume the union of elements in the collection equal to all of X. Now, are you following? Each U is in tau A. Therefore, the union must be in tau A. Therefore, empty set will be there. Sorry, the full set X will be there. And empty set is there because I can always take union over the empty collection. Okay. So we put extra restriction. Okay. Assume that strictly speaking, this is not needed for what from what we are going to collect, but it's always good to assume that this happens. Okay, please pay attention. I am going to assume my collection A has the following property. What is the property? X is union of elements coming from A. If you want, let me just put in terms of A in script A, this is must be all of X. This is our assumption hereafter. Assume always hereafter. Okay, when I want to talk about the smallest topology containing A, namely tau A, I am assuming A has the following property, this property. Right. Okay. Next, right? Next, let's take something like A and B are in script A. Then script A is contained in tau A. That means A intersection B must belong to tau A. Do you understand that? Yeah? Yes or no? Right? And for that matter, since the tau A is a topology, therefore if we take A1 into AN times AN, or not times, up to AN, then A1 intersection A2 intersection AN must be in tau A. So this must be true for every number. If you want n greater than or equal to 1, natural number n, and for every A1 AN, right? You take any n elements, arbitrary elements of A, their intersection should be there. It may be empty. You understand? If it's not empty, again it's a non-empty set, it has to be in tau A. Do you all follow that? Yeah? Yes or no? Now in particular, if I take n equal to 1, all my A1, A2, AN also in tau A. Do you follow that trick? So if I take n equal to 1, that means for every A in script A is, the intersection is just A itself. Okay? Please pay attention. Yeah? So what we are going to do is, I am going to look at tau naught equal to set of all subsets U of X, so that for every X in U, now understand, okay, there exists a finite collection A1, A2, AN in script A, so that X belong to A1 intersection A2 intersection AN, and that's contained in U. Please pay attention. Go back to what we did. For example, let's look at this case where I had a left trace and right trace, right? Okay, and suppose I take U, okay, usual open to in the open the usual topology, right? For each X in U, what do I know? There is X minus epsilon to X plus epsilon, which is contained in U. But this I can write it as what? Minus infinity to X minus epsilon intersection X plus epsilon to infinity. Oh no, I think X plus epsilon to X minus epsilon to infinity. Yeah, this is nothing other than this. So these are our original things in A script A. Please, I am not giving a linear lecture. I want you to think, because I also think when I am explaining, I want to explain that, so I give an example to make understand. You follow that? This is what we are trying to do. Yeah, so if please internalize. So I have a set X, and this is set U. I want to show this open. What should I do? You give me any X in U, then what should I do? I have to find something like A1, A2 and A3 and so on, that intersection. Okay, so okay, let me just look at a slightly better way. Maybe I should draw a linear thing so that it will be easier for me to draw. So I want to show this U is open. So you start with any X here. Then what do I do? Okay, I want to say for each thing, okay, this is an element A1. Okay, this may be my element A2. Okay, this may be my element A3, therefore this is the final thing. You understand? That's what we want to do. So we show that this is, so we will show that tau naught is a topology. Okay. Now empty set belong to tau naught as usual. Okay. Why? Because I only have to take empty color. You give me an X. Okay. To show empty set belong to that, you have to, what do you have to do? If it is not, then you have to say there is an X so that I cannot find any sub collection like this. So that is false. You follow that? Therefore empty set belong to that. X belong to tau naught. Why? Give me any X. By assumption there exists a in script A, so that X belong to A and A is contained in X. Why? Our X was union of A is in script A. Yeah, therefore this is true. Now let's take arbitrary thing. So let UI be a collection of tau naught. Then I want to know union UI isn't tau naught. Yeah. So how do I prove that? Start with any X. That means there exists an I. That X belong to UI. But then what do I know? UI belong to tau naught. If UI belong to tau naught, X is an element, there exists a subcollection A1 to AN in script A. This N may vary. You understand that? Depending upon X, and the A's will also vary, the number N may vary. Usually what I do, I will come to that. Okay, so that X belong to A1 intersection AN, that is contained in UI. Therefore this is contained in union UI I in script I. Yeah, so this is done. Let me say, usually when I teach in a class, I will not write A1 to AN. I will simply say tau naught like this. U, okay, a subset of P of X, so that for each X in U, there exists a finite set of X, okay, where in script A, so that X belong to intersection A is in the finite set, and that is contained in U. That means the finite set will depend upon Fx. So how many elements are there? That may depend. And what are the elements? Again, that may depend upon X. You understand? Pause, review, proceed. So in the master's degree, one should avoid usually a finite set, meaning you should not write x1, x2, xn. That means there is an order among the elements. In general, it may not. Anyway, so let us quickly wind up. So I am running out of time, so let me quickly wind up. Okay, so I have tau naught like this, right? So what did I do? Tau naught is closed under arbitrary unions. Okay, now let's look at intersection. Suppose U, V are in tau naught, then U intersection V. Now what do I know? Start, I want to prove whether it's in tau naught. Yeah, so let X belong to U intersection V. What should I do? To show U intersection V belong to tau naught, what should I do? Take any X in U intersection V, then I have to find a finite collection of X, so that, okay, the finite number of elements in that subcollection of X that contains X, and it's contained in your U intersection V. You understand? Now let me just look at, since X belong to U and U is in tau naught, there is a finite subcollection F1 of script A, right? If you want, call it A1 to AM, so that X belong to A1 intersection A2 intersection AM, and that is contained in U. And similarly X belong to V, that means, and V belong to tau naught, that implies there is a finite subcollection F2 in script A, call it B1 B2 Bn in script A. So that what happens? X belong to B1 intersection B2 intersection Bn, that is contained in B. Now what is the one you will take? Now X belong to A1 intersection AM, intersection b1 intersection bn, that is contained in u intersection v. Is that clear? And where are these elements? They're all in script A. How many are there? Finitely many. Therefore, okay, tau naught is closed under finite intersection. We proved only two elements, but as usual induction shows finite intersection, right? Okay, so what do you think I have proved? I have proved tau naught is a topology on X. And is it clear A belong to this? Yes. Why? Because why does, given any A in A, why does A belong to tau naught? That means for every X in A, I have to find, I can take my collection to be singleton A itself. X belong to A and A is contained in A. You understand that? I should have something like A1 intersection AM, right? But I am going to take M equal to 1 and A1 equal to A. Are you clear? Therefore, this is already a topology. So tau naught is a topology containing A. Now notice that tau naught is contained in tau A. Why? How did I conclude? Start with any element A. Okay. Start with any element U in tau naught. I want to prove U is belong to tau A. That is obvious. Why? Notice that U, yeah, is that clear to all? I want to prove U is in tau A, right? Yeah. So what should I do? Why it's the smallest topology? Is this okay? Now, sorry, I don't need it. Already I proved it. I'm sorry. See, I already proved tau naught is in tau A and A is in contained in tau naught. And tau A is the smallest topology. Therefore, tau A equal to tau naught. Okay. Please again go through. This is the most important result of today's lecture. So if you give any arbitrary collection of Px, the smallest topology containing A tau A, I will assume oppose union A in A is X. Okay, this assumption is already there. Okay, is defined by all subsets U of X, that for every X in X, every X in U, what should I find? I want to find a finite collection A1 to AN where in the given family with what property? So that X must be in A1 intersection AN and this subset should be contained in U. So we have very concrete description. Yeah, you will see the power. Okay, usually textbooks and teachers will play with words basis, sub basis, the basis for a topology, a basis for some topology, etc. Do not worry about it. I will come to that. Okay, but this gives a description. Okay, if I want to show what are the open sets, it gives a recipe, it gives a technique, it gives a tool how to show something is open in the smallest topology tau A. What all I have to do is I have to find a subcollection, finite subcollection for every X. I have to find a finite subcollection A1 to AN, so that X belong to A1 intersection A2 intersection AN, that is contained in U. Remember, this is something similar to earlier things where we define, okay, like a metric space open set for each U, for any X in U, there is an open ball, X belong to BXR and BXR is contained in U. Something similar. Yeah. Okay. So please go through this. I know it would be a little overwhelming, but believe me, this is one of the most important constructions in topology. And go through this at least twice. I have taken pains to give a lot of simple examples to make you understand what are the issues and also to get over the fear of complicated notation also, right? I hope you understand this. Go through it. Okay, discuss with your friends most. Okay, you will enjoy. And finally, remember the last description of tau A. That's the most concrete. Okay, most of the textbook will be, write a very complicated things, giving a lot of terminologies, etc. So don't worry about. You will see this tells you exactly what needs to be done. Okay, believe me. Okay, take care, stay safe, we'll meet again.